part 4. Yeah. So just to revise, sort of, just to give the context of how we are sort of flowing in the large scale structure, we started by talking about, okay, what are all different kind of things we could do in terms of cosmology, modified gravity models, what are the state of the art. I've already showed you those results. And pretty much anything you're working on, whether it's dark matter physics, dark energy models, late time evolution, non-trivial models. If you're interested in non-Gaussianity, something we're listening to in the morning lecture also, all of that will have, large scale structure will be able to say something about pretty much all of those things. So all of you will have some interest in this kind of thing. Then in the second part, we talked about what kind of measurements we do, different kind of filters, different kind of survey we can do, and what are the complications with some of them, how the cost varies depending on what you want to look at. And we also talked about Fisher matrix forecast, how to sort of go about using Fisher matrix to figure out if you want to do a constant particular model, what kind of measurements you'll need. And I also showed you some Fisher matrix forecast, and I also told you that I will share the script to create the kind of plot I created. So I've sent it on Slack, which if you're on Galaxy Service Slack, I sent a message. There's a link from where you can download this script and run it. There's not much documentation, but if you understood what I talked about in terms of how Fisher matrix works, you should be able to just run it and make the plot. You might need to install some library. So if it complains about some library, just install it. And then in the part 3, we started talking about, okay, from something like distance measurement, where we talked about Fisher forecast, how do you really constrain dark energy equation of state with using things like Supernova Cosmology or Baryon Acoustic Oscillation, which are two of the state-of-the-art methods to constrain this kind of thing. And including, I showed some results from recent DESI survey, what are the kind of constraints we have obtained. Now, today what I wanted to do is I wanted to sort of change the flavor a little bit to give you what kind of other things you can measure with this kind of survey, and maybe focus on more on, let's say, on the gravity side of it rather than the background side of it, which is what we have been focusing so far, right? So if you think about it, and the major thing I'm going to go into, so there are a lot of topics, but I'll be largely talking about redshift space distortion, which you are also going to measure in the tutorial, hopefully in the evening today. And so this is one of the way to test gravity at large scale. So just to give you an overall background, which most of you are already familiar with, if you start with general relativity, if you want to think about testing general relativity, there were sort of 3 kind of tests were proposed when general relativity was proposed at that time. The first one was perihelion precision of Mercury itself, and the prediction was spot on, and so it was able to, actually not the prediction, but the explanation was spot on, and so it was able to explain that. Second was the deflection of light. So all of you must have heard of these expeditions during the wartime, and then there were measurements of deflection of lights around stars. This is one of the image from that. You can't really see what was measured in this resolution. You have to look at more carefully, and that was also very great. And then the third part was prediction of gravitational redshift, which was measured a bit later in 1960. There was an experiment in Oxford where they basically did a drill hole in the ceiling of several floors of the building, and then they did an experiment where they passed a photon from the bottom, catched it on the top, and then passed it from the top and bottom, and this was a very precise measurement. So they could measure frequency shift of 10 to the minus 15 in 22.5 meter height. So this was one of the very first measurement of gravitational redshift. Just to tell people who may not have heard of this so much, if you have any sort of, let's say, a massive body and it's going to emit, for example, sun, it's emitting light. This light is going to travel out of the gravitational potential well of this massive body, and it's going to start shifting. This shift shown here is, of course, is highly exaggerated. the amount of shift you are going to see from sun is very tiny. You're not going to see such kind of color shift. You're going to see much smaller, but that's what we're talking about. And so all these three tests were sort of passed with flying color, and this is one of the statement Einstein himself made, that the chief idea is the logical completeness, and any of the tests, if it fails, then the whole theory has to be discarded. So we have been still looking for where it fails. You might have heard of tension, and some of that might be coming up, but only time will tell, and so we need to figure out what are the better ways to test these things at higher precision. Okay. So how are we doing this kind of test now compared to before? So we are still trying to do essentially perform the same three kind of tests with different kind of measurement. One of them is what we call redshift space distortion. So this is galaxy correlation function, which all of you now should be very familiar with, as a function of perpendicular separation and parallel separation. And what you see is an anisotropic distribution. I'll talk about how that anisotropy comes about, but this is a measurement of essentially growth rate, which is a measurement of the strength of gravity. So matter-matter interaction term is what you can measure with something like this. You could also measure gravitational redshift in large-scale structure surveys. I'll also talk about that using the same kind of quantity, which is clustering, as a function of parallel and perpendicular separation, and you'll see this kind of effect, which is again highly exaggerated compared to the realistic measurement. And this something is going to allow you to test the third test I talked about, which is gravitational redshift, again at very large scale, at cosmological scale. And then finally, you can look at gravitational lensing, which is going to look at the interaction of photon, or the light bends around massive objects, and you can now perform much precise measurement at very large scale. And so this is again going to allow you to test gravity in terms of the photon matter interaction. So during this series, I will not talk about lensing so much, but there was an IAGRG school, I think 2020 probably, where Surud More gave a very extensive lecture, and it's available on ICTS YouTube if you want to, including how to sort of even do measurements of some of these things. So there were tutorials and everything is available. No, it's not available on YouTube? I thought it was. Okay. Okay, but what I can point you to is there are lecture notes and slides are all available on. So this is something I've seen because he has sent me. So I can point you to that in case YouTube lectures are not available. And so you can go over that if you're interested in weak lensing. So this does a very good job of all the details about weak lensing. Okay, so now let's focus on one of those things, which is redshift space distortion itself. So what is going to happen? All of you, not all of you, at least some of you have already measured this kind of quantity, right, in a simulation just yesterday. What is this? This is correlation function as a function of perpendicular and parallel separation, where you're saying that if you have an observer, there's a pair of galaxies, you define a line of sight, you deproject the distance in perpendicular and parallel ways, and then you plot. You essentially count number of galaxies and estimate volumes and calculate this quantity using an estimator. So I guess some of you have already made this kind of measurement, and what you find is that these contours are circular, and so it's an isotropic thing. But if you have to go and do this kind of measurement for real data, you'll not see something like this. What you're going to find is something like this. This is in fact a real measurement from a survey called EBOS of correlation function, and what you find is that it's no more circular, it's somewhat elliptical. And so why does this happen? Why is there anisotropy in correlation function? When you look at pair of galaxy, line of sight seems to be a special direction. The clustering seems to follow different relation with distance in line of sight versus perpendicular to the line of sight. So that's why you're seeing this ellipse. So the reason it happens is because how we measure distance. It's ingrained in that procedure itself. So this is just a fly-through of one of the very old, I think it's more like 15-year-old video from Sloan Digital Sky Survey, where you're flying through a real universe, in fact. And each of these galaxies are real galaxies observed through this survey, where we are able to place them in three-dimensional space because there is a spectra for each one of them. So we are able to measure redshift. All right. And so if you remember, again, if you can measure spectra, you can measure several features in the spectra, and you can sort of look at what is the observed wavelength compared to what your expected emitted wavelength, and that will give you the scale factor at which that galaxy is residing in, and so that light was emitted. And that will give you redshift, which you can convert into distance. So we have seen this now several times. Now, what is going to happen in realistic scenarios that these galaxies are living in various different environments. So dark matter halo, which are shown as curvature in the space-time itself in this image, but they are not sort of just sitting there. They are interacting with all the environment there. And so because of this interaction, they will have peculiar velocity. So they'll be moving around in the space. So they might be orbiting in the potential, or they might be sort of falling into another halo, or if at large scale, they might be feeling the overall large scale gravitational pull, and so they might be falling into each other. And so there's an effective peculiar velocity for each of these galaxies. Now imagine if something is moving, what is going to happen if a moving object emits a light? So if a moving object emits a light, you are going to expect somewhat similar to Doppler effect. So I told you now there are three reasons so far due to which wavelength of light can get shifted after it's emitted. The first one I talked about is cosmological expansion, right? So that's what gives you distances to these things once you have a cosmological model. I also mentioned about gravitational redshift, which is also going to introduce another shift because it has to climb out of the potential veil of this dark matter halo and the galaxies. And the third one is there is going to be peculiar velocity. And so if peculiar velocity has some component along the line of sight in which you're observing, then that's again going to shift your things. And so how will a survey look like if you were to observe it in redshift space? So this is a simulation for something called 2DFGRS, so 2-degree field galaxy redshift survey. So this is an old survey, but this is a simulation. This is not real data. This is a simulation where each black point represents a galaxy. And so what we are showing is along this axis is redshift or distance, and this is one of the angle, and you take a thin slice from under the angle. So you're basically they're taking a thin slice of galaxy and plotting it here. But this is how it will look if you're able to measure true distance of these objects. But if you're only able to measure redshift, which is combined with peculiar velocity, so there's an additional shift which you do not know, which is not in your redshift distance relation, and you behave as if like there's no such effect. Okay, and you just use the redshift to calculate distances and make this plot, you're going to see something like this. So you see there is an interesting difference between these two. And so mostly what's happening is that things are getting elongated along the line of sight because that's the only velocity component you're going to be sensitive to. There's not going to be any lateral movement. It's only going to move things along line of sight. Because there's an additional term in your redshift which you're not accounting for. And because of this, now line of sight becomes a special direction, and hence it introduces an anisotropy. So when you look at pair of galaxies, the distances along line of sight is not the true distance, it's true distance plus some component of what is the infall velocity of these things, or pairwise velocity of these things with respect to each other. And so that's what gives you this distortion in correlation function, which we are going to measure later on in the tutorial. Yes. These white surfaces are contours in the correlation function. Yeah, it has some fixed anisotropy. Why is it so? Okay, so white is fixed. So when you say first of all fixed anisotropy, then what do you mean? Is it like constant as a function of scale? Is that what you mean? Anisotropy is measured by L. Yeah, so I'm not really following your question, but maybe let me try to explain this a little bit more. So what is happening is that so actually this is supposed to be a circle, but when you look at the pair in parallel separation, because of the velocity term, there's a large scale infall. So galaxies are infalling into each other, they will appear slightly closer, and so it will come closer. And so this is what is happening, but how much closer it's going to come will be function of distance itself. So the ellipticity of these different curves are not is going to be not necessarily constant. In fact, if you are modifying gravity where there's a scale dependence effect of gravity, you're going to see that here as well, that kind of thing. Does that answer your question? Okay. Yes. Yeah, so that's a great question. If you're thinking about U as a reference, so let's say you're calculating 2-point correlation function in which one of the point is U, then that's not what it is, right? This is 2-point correlation function where each of those points is living in the sample. And so now what you're talking about is pair separation of two galaxies, both are living in the same gravitational field. Now these two galaxies on an average will not have zero velocity with respect to each other. So these two galaxies will have essentially some non-zero velocity, which is the effective gravitational pull. So there will be all of it is going to interact with everything else, but there's going to be, if you imagine just these two galaxies on an average, they are going to get attracted towards each other as well. So there's going to be infall. So that's the infall you are seeing. So we are not measuring this correlation function with respect to us, but we are measuring this with respect to each other, the galaxies itself, and all of that is in the same field. Right. So symmetric across vertical axis. You mean why positive and negative are same? This axis you are talking about? Yeah. Mm-hmm. Right. Yeah, because I guess you are thinking about it will not be symmetric because of some reason. So what is important in terms of thinking about, if you think about the velocities, infall velocity of a pair of objects, it's really the distance, right, in standard gravity. There's nothing else. So now if I replace these two, this is completely symmetric under the replacement. And so you don't expect this to be asymmetric in that kind of configuration. So gravity doesn't care, right? If you pull them this way, if I replace the galaxy which I'm looking at first versus second, I should get the symmetric thing. So that's why it is symmetric. So you don't, in fact, you don't expect any asymmetry along line of sight. But actually for this plot, the reason it is symmetric is because the way it is measured is that we only measure one of the quadrant and we flip it and to show it all other quadrant because we expect symmetry. So this will be perfectly symmetric. Is it computed for each what? Sorry. So we are not talking about clusters at all here. We are just saying we are calculating 2-point correlation function of a sample of galaxies. So it's all the galaxies in the sample. It's exactly the exercise you're doing in the tutorial. There's nothing different. So we are not differentiating. We are not looking at massive halos, groups, or clusters. We could also do that, and that also has some interesting effects. But this is like 2-point correlation function of all the galaxies in the sample. Right. So now there are sort of two ways to think about how to model this. I will try to show both of them. One is thinking more in the Fourier space, other in the configuration space. Just to give you an intuitive feeling, I'm not going to work out in detail how exactly you do this because anyway, the calculations I'm showing you is linear order and that's not good enough to do any analysis. If you really want to do this, you have to do higher order perturbation theory, and so you have to spend time and carefully go through that. Right, but to give you an intuitive idea how this thing works. So what is happening is that separation, which S is denoted by in redshift space, is real space separation plus the component of velocity is scaled by scale factor and Hubble factor to convert that into distance effectively. So how does the velocity shift correspond to distance? And so this is what is going to be the transformation in terms of real space to redshift space. So in real space, if a pair of galaxies separated by R, in redshift space, they will be separated by S, which will be dependent on the velocity of these pair of galaxy. So relative velocity of the galaxy decomposed along the line of sight. So that is the only component which is matters because we are not sensitive to the perpendicular component, right? And so if you do this coordinate transformation, and if you say that, in this coordinate transformation, I am not going to lose or create galaxy. So none of this should change galaxies. The number of galaxies should be same before and after transformation. So you can essentially conserve this by saying that the density times volume element and density times volume element integrated. Yeah, sorry, there's a missing integral. So integrated version of this, not in the local, but the whole volume is going to be constant. So they are going to be same. And so if you sort of take those two ideas and work out in linear theory, if you have matter distribution where the velocity is essentially nothing but the gradients of the density, and so everything is known once you have the matter distribution, the overdensity in redshift space is related by overdensity in real space times operator, which is essentially what we call growth rate. And so this is the term which is sensitive to gravity. Growth rate times the operator. And so this operator is explicitly given here. And if you apply this and work out a few lines of algebra, what you're going to find is that this will eventually give you this relation. So this is what we call Kaiser formula. So what this is telling you is that the matter power spectrum which we have been talking about, which is a function of k, now will also depend on angle of the mode, right? So mu is the cosine theta from the line of sight. It will also depend on the angle of the mode, and so it will be anisotropic now. So the observed matter power spectrum of our galaxy power spectrum is going to be both function of k and mu, where the mu dependence comes from this f, where f is the logarithmic derivative of growth rate. So that's the term which we are trying to measure. So this is not just this is a little bit of detail. This is not entirely, this conservation I told you is not entirely true in realistic survey. The reason for that is when you are going to do this survey, if you remember for a spectroscopic survey, we just don't observe all the objects. We have to first apply selection. So you do photometric survey, and then you try to select objects which you want to observe because you want to optimize several things. So when you apply this selection, because of how the sort of brightness looks like of these objects as they are moving along the line of sight, what might happen is that in real space and redshift space, if you were to apply the same selection, you're going to find different number of objects. In fact, you can do that calculation as well for a particular survey. What this is showing you is that in some combination of color, so I've told you about magnitudes already, and so the differences of magnitudes is color. So it's some combination of magnitudes observed of a galaxy. There are two magnitudes, and if this galaxy is moving along the line of sight at different velocity, the velocity can be as much as 1% speed of light. So they are going to move in this space. They're going to move in the magnitude space. And so let's say if I'm saying for my spectroscopic survey, this is my boundary, I'm going to select all the galaxies under this yellow line, then what might happen is that because of change in magnitude, because these galaxies have peculiar velocity, they are going to get relativistically beamed, and so the flux can get enhanced if it's moving towards you. If moving away from you, it can get suppressed, plus there's going to be shift in the wavelength. So all of that is going to can move things in this space, and so a galaxy can move in or move out of your sample. And so this is not strictly true for a color selected sample like we do for a spectroscopic survey, but it's a tiny effect. It's like 0.1%, and so it doesn't matter so much, but we have to be careful about that when you're doing very precise measurement, 1% measurement. Okay. So now I hope you have intuitive idea about why this distortion is happening, and you have at least you know what are the basic principle to derive this thing, which is called Kaiser formula. So this is what we call Kaiser formula by famous scientist Nick Kaiser, who was in fact here at ICTS last year during a school. So you can look at this where the f is essentially logarithmic derivative of growth rate, and now this is going to be function of what your gravity theory looks like. So for different models, it will look different. For lambda CDM, it looks like omega matter at scale factor e to the power 0.55. But for example, for f of r gravity, this will look different. The factor 0.55 will look different depending on what f r naught value is. There's another thing which you might want to keep in mind is that this matter power spectrum, the amplitude of the matter power spectrum itself is a function of what is the initial perturbation, initial matter power spectrum amplitude is, which is often measured in terms of sigma 8 or ACE alternatively. And so that is one thing which we are going to be completely degenerate with. And so with a measurement like this, you'll never measure f, at least in the this kind of formalism, and you're going to measure f times sigma 8 because sigma 8 is hidden there. So unless you know sigma 8 from another way, typically you measure it from lensing or CMB, all you're going to measure is a combination of f and sigma 8. Right. So this is going to change very soon, but so far, this is the current status of measurement of redshift distortion across the cosmic history. So you can see this is from an old survey, not so old, but still old survey, Sloan Digital Sky survey. This is starting from very low redshift, something like 0.07 to 0.2, to going up to 0.4, 0.5, 0.7, something like redshift 1, and then this is close to redshift 1.5. And you can see this anisotropy in all of this. So we can actually trace this peculiar velocity I'm talking about across the cosmic history. And so I can measure growth rate and then test how that growth rate is consistent with what we expect with different models. Right. So, okay, that's great so far, but I have only told you half of the truth so far. So I've showed you pictures. So this is again from a simulation, where you're looking at the same kind of quantity but with different color scheme. But this is only half of the picture, because the realistic measurement would look something like this. So you can see there's a remarkable difference between the left and right. And so on this plot, you see this stretching of correlation function at very small scales. And this is what is coming from basically highly nonlinear velocities and what is called finger of God. And this becomes a problem because the Kaiser formula I told you do not account for this at all. So there are prescriptions to account for it, but that's the hard part. And so you cannot go to very small scales if you were to use a model, the kind of model I described, or even perturbative order model of that. And so what is this finger of God? Like, what is happening in terms of physics here? So there are sort of two regime of redshift space distortion. So if you think about a dark matter halo, there are galaxies, and then let's say there's another dark matter halo and there are multiple galaxies. When you look at a galaxy across dark matter halo, this will be in large scale. So that's what I was showing so far. This size is roughly, if you have a very big halo, then a megaparsec, right? Everything, so all halos are below than megaparsec. All of the scales I was showing so far was 100 of megaparsec. So this scale is tiny compared to what I was showing. And so what you're seeing is you're always seeing this sort of two halo thing. So you're looking at objects separated by far distances, and so there will be some net infall of these things. So there will be whatever random velocities, but there will be some net infall which you can project in the line of sight direction. And so that infall is what is going to make this thing a squash thing, an ellipse. So this is what I talked to you already. But what is going to happen when you go to very small scale? So roughly a megaparsec scale. So if you look at, this is 0, this is 5, this is roughly 2 megaparsecs. So that's the regime where things are getting extended. This is very close to the scale of the halo. And so when we are measuring things within same halo, when you're looking at galaxies within same halo, now what do you expect to see? When you have galaxies in the same potential well of the halo, typically what is going to happen is that if these galaxies cannot stay stationary, first of all, they cannot just be at some same point in the halo because they are at least experiencing the gravitational force from the halo itself, right? So they will infall if they are stationary. So if they are, they has to stay there for a long time at certain distance rather than just infalling to the center. Typically, they are going in some kind of orbit. So this orbit could be random depending on how the whole process happened, how the galaxy came about, whether it formed within the halo or it fell from the other side. And so that will effectively give you what we call velocity dispersion, right? So varialization, velocity dispersion, you have heard of all of these terms. And so what happens is that typically all these orbits, which may not be circular most of the time, it might not be even circular orbit most of the time, but all of these orbits will effectively give it a temperature to the galaxy or a velocity dispersion to the galaxy, which will allow it to be a stable structure. And so what you're going to measure is not an infall, but a velocity dispersion. And so the relative velocity will be proportional to what is the dispersion of the halo itself is. And so this velocity can be large depending on what you're looking at. And it will be a function of what is the host halo in which galaxies are looking at. So by looking at a structure, so because this is a dispersion and this can be large, this is getting a stretch, right? So yeah, so if you, so first of all, let's say you are looking at this halo from somewhere and you forget about the observer. Now, since these are in all different various kind of orbits, what you're sensitive to is always the velocity dispersion. And so it doesn't matter whether the two galaxies are both away from center or one of them are at center and one of them is away from the center. You'll look at all different combination. In fact, you don't know which galaxy is at the center and which not. In this exercise, I've never told you that galaxies are at the halo and you can choose things, right, when you're doing two-point function. And so it doesn't matter in terms of what combination you're going to look at. In theory, when you're going to do this calculation, then it will matter what kind of galaxy you're going to look at. And then the second thing is you are only sensitive to the line of sight velocity. So in fact, what is going to happen is that you have to choose where the observer is. Let's say observer is here. And so this galaxy might have whatever velocity in terms of 3 dimension. It's only the line of sight component of the velocity and the relative difference of those two is what you're going to be measuring. So only the line of sight velocity is sensitive, and that's what you're going to measure. Depending on what is the total velocity dispersion, effectively what you're doing is you're sampling. So let's say the halo is, if you are sitting in the rest frame of the halo, the mean velocity is going to be 0 and there's some dispersion. This dispersion itself you can calculate by applying virial theorem. So you know if there's a density distribution, what will be the width of that. So what you're sampling is essentially each pair is going to be a sampling from that distribution. Mm-hmm. Yes. No, so I think maybe you're thinking about that you're measuring only one of them, but that's not the case, right? So you have many of them. You have all different combinations. You're statistically averaging over all different combinations. Now the question actually will become interesting in the regime where you say, okay, is this halo isotropic or is this halo anisotropic? If halo itself has a shape to it, now this shape will imply that there's a velocity dispersion will also be in different direction. And now in this case, whether the halo is aligned, major axis is aligned towards you or not, you'll measure different velocity dispersion. So that will be the case, but we are not thinking about one pair or one halo at all. We are thinking about average over all the galaxies in the universe. So even if individual halos are anisotropic, these directions will be oriented in different ways, and so effectively the total you're going to measure will be isotropic behavior, right? Otherwise you have to account for, you do have to actually, in fact, if you want to model this at small scales in detail, you do have to account for anisotropy as well, velocity anisotropy. I think you had a question. So if if it so happens that all the pair you're observing in this thing is always, the total velocity is always aligned towards line of sight, then you would expect, since total velocity is always aligned to the line of sight, the effective mean dispersion can be larger. But if you're working in the picture where I'm thinking that all halos on an average is isotropic, so we know that halos can be oblique, but that oblicity is small. If you're going to do very high precision measurement, then we do expect to see that effect of that oblicity. But so far, all the measurements we have is not sensitive to that. So in this case, what is going to happen is that if you know estimate of the halo mass, and then convert that into the velocity, and if there's a significant anisotropy which you are sensitive to, those two things will not match. Mm-hmm. Mm-hmm. Okay, so how would no? So these objects will have all different velocities. So that part is right. But then effectively, since you are looking at several pairs, you are sampling from this distribution, right? And so there will be some fraction of object which will have large velocity, and that large velocity will give you stretching. But not all of them will have large velocity, which is why the amplitude at this scale is still high, but it just gets stretched. How much stretching will happen depends on the distribution, in fact. What is the distribution? Yeah, and you're sampling from that distribution. So these circles, I'm drawing these circles as a halo radius, yeah. No, galaxies. No, so did I not tell this already? Okay, so like what is our picture? So our picture is that halos are very big, right? Inside halo there can be several galaxies, and inside galaxies there are stars. The scale of, so if galaxy is a kiloparsec, halo will be of the order of megaparsec, right? So 3 order of magnitude or 2 order of magnitude different scales is there. Stars is going to be much smaller. Right. So this plot is from a simulation, but actually, and the data I showed you earlier, they don't show this kind of feature so pronouncedly because I'm just plotting things at very large scale. In fact, those things are there, but it's at very small scale. You can't see them because we don't have the resolution. So remember, we did this grid correlation function. If you don't have the resolution, if you have not sampled things fairly, you're going to miss the feature at the scales smaller than your resolution. And so that's why we don't see this feature in this picture. But then you can see this if you actually plot them more carefully. This is now measurement from DESI data where you see this stretching I'm talking about. And what you also see, so these are across different redshift of different kind of galaxy. Now different kind of galaxies are living in different average halo masses. And so you expect, if I told you what makes sense, then this dispersion, the nature and the amplitude of this dispersion will look different in different kind of sample. That will tell something about, okay, what kind of average halo mass these things are living, what kind of velocity sampling they are doing. And that's what we see. So we see that something like BGS, which is living in a much deeper sample, so living in a much smaller halo, compared to LRG, which is living in 10 to the 13 halo, has significantly more dispersion at center, so significantly large finger of God. And then this sample, which is 10 to the 13 halo, is much more massive than this kind of sample, emission line galaxies, which is living in something like 10 to the 11 halo. And so that's, again, smaller. And then you don't see much here. This is quasars, simply because for quasars, we are extremely short noise dominated. So it's a very sparse sample. It's very rare to have 2 quasars in the same halo in this kind of sparse sample. So you don't really see the effect of finger of God very pronouncedly. You mostly see noise. So this thing basically goes to close to 0. It's black. So all of that I told you is not just a picture. We have seen the evidence of this in data as well as in our simulations, and people have measured this. So now let me sort of give you another view of how to think about modeling redshift space distortion. So this is the second view, which is going to be in configuration space. Yes. Sorry. Yes. Second effect. Sorry, I'm not sure what you mean by second effect. Yes, so what this picture is, in fact, so this is to illustrate. All of this is sort of makes sense because in this picture, what I have done is I've said that in each halo I can have only one galaxy. So I've forced it to be just one galaxy. Now you are not sampling one halo term at all, and so there is no finger of God. In fact, the correlation function goes to 0 here, which is why you see some weird feature. It goes to a very small value at very small distances. Now, in the same thing, now I've allowed multiple galaxies to be in the same halo, and so now you see the finger of God effect. And so that's why this explanation makes sense in this picture. Right. So now we can think about, okay, what's happening in terms of redshift distortion, a little bit in configuration space is the same kind of idea what I told you for the real space. You take the position, so let's say S parallel and S perpendicular, you look at pair of galaxies. Now you can write redshift space position is equals to R plus V times V, projection of V along line of sight. And this will effectively mean that a pair which was separated at with distance r at S perpendicular and S parallel was actually here, will appear here depending on the sign of this velocity. And so what you're effectively doing is you're taking the correlation function and then you're relabeling your positions. If this was the only thing, if it was only shifted, then you're effectively relabeling your position. This R and S transformation, if you know what is the V as a function of scale. And that is something you can calculate in perturbation theory for any particular gravity model. But what is going to happen is that in large scale structure, since it's not just one pair of objects, there's a lot of other structure around it. And so this peculiar velocity V12 as a function of radius is going to have lots of dispersion depending on which part of the universe it's living in. And so it's not just one mean velocity, but there's also dispersion. And so what you're going to say is that some of them might move here, some of them might move here, some of them might move there or here, depending on how much is the dispersion in this mean velocity. And so you can model that dispersion by essentially assuming a Gaussian, which is a good first approximation. It's not completely, because this dispersion is not Gaussian. It has non-Gaussian terms. But to first order, you can model it as a Gaussian and do this integral to get here what is the expected value of correlation function in redshift space. In this picture, again, I'm ignoring effect of finger of God to begin with. But what is finger of God going to do? So finger of God, what is going to do is that at small scales, it's going to say that the velocity dispersion is larger than this large scale velocity dispersion I'm going to do, and this is going to dominate at some scale. So if you modify your velocity dispersion as a function of scale, at small scales you say there's an additional term, then that is going to mimic something like this. So in this integral, if you just modify the sigma 1,2 with additional term, which appear only at certain small scales, you're going to actually produce both finger of God and large scale distortion. All right. So I hope this gives you some understanding of one of the technique we use from large scale structure survey to constrain gravity. But I've told you sort of a simplified story, and if you want to do the full thing, which I don't have time to talk about all the different steps, but if you really want to do the full thing, what you need to think about, first of all, non-linearity in the matter power spectrum itself. You need to solve for those. Then I've talked about linear bias, but then you have to also include nonlinear bias in that. And then to include RSD, you need to solve for what is the velocity field look like in this setup. So you have to perturbatively solve for velocity as a function of distance and velocity dispersion. And at that point, then you can apply the integral, which I showed you in previous slide, if you have all the ingredient worked out, and you can predict this. And so this is what will then allow you to infer any sort of quantity like growth rate or velocity dispersions of these galaxies. So there is sort of approximations in each of these things, and so when we are analyzing this in real data, we have to rely on simulation to test all of these approximations. Especially if you're using perturbative approaches, you have to say, okay, to what K mode your perturbative approach has converged and give you unbiased result. And so that requires a lot of simulation work, which is what people do in many of these collaborations to figure out to a very high precision, because our measurements are getting precise and precise. We're talking about measuring this quantity to few percent precision, which means any of these ingredients should be converged at sub% level. And so that needs to be tested against simulation. Often that's a very computationally expensive work as well as technically challenging. So to plot this, you're doing the measurement which is already convolved with the bias, right? So if you have the data, you can just measure it and plot it. You don't need to know anything about the galaxy bias. But when you're writing down on the model, and let's say you want to make a similar plot with model which looks similar to this, then you need to know what is the bias scale dependence of the bias for the model. Okay, so that basically covers how do we measure growth rate from a survey and what are the challenges, and at least give you some simple picture of how do we model it in linear theory, as well as how to measure it. So the details about, technical details about how do we measure it, we'll do this in the tutorial. So you're going to produce plots similar to what I showed you with redshift space distortion, with simulation as well as real data. But once you have done that, now what are you going to do? So there are sort of several ways to, or several regime you might want to work on. This is one of the popular one in the community right now, where if you want to, let's say, think about testing gravity, you can start with very general action, and you can say, okay, I can write down all scalar tensor modification in this fashion, and this is what is also known as Hordinsky formalism, and I can write down the metric and look at what are the two different parts. And so in a very generic sense, this is equivalent to saying that my metric potentials have two functions, which is mu and gamma. So I'm introducing two new functions. If you set gamma and mu to 1, then you converge to GR. Now these two functions, mu and gamma, can be function of scale factor or redshift as well as scale in a most generic way. So the goal becomes then, can you constrain the functional form of this with the data? And since our data is not very precise right now, you cannot constrain the full free function. You have to propose some kind of functional form. And so this is one of the functional form which has been proposed in this particular paper, Visva-Bharati, which is based on certain arguments about symmetry and the kind of models which are more reasonable, where you don't have ghost and physical behavior and things like that. There are also some constraints on this parameter. And so once you parameterize it, now you can look at parameters like beta 1, lambda 2, or you could also say that, okay, there is a overall scale factor, and then you can measure what it is. Or the most simple you could do is, let's say this is constant. This is not function of scale at all or redshift at all, mu naught and gamma naught. And then you can try to constrain that. And so all of these can be constrained to different precision. And so the reason this can be constrained, if you were to plot growth rate, which is what you're going to measure with redshift space distortion, right? So this is the quantity which was there in my Kazar formula. If you plot growth rate as a function of scale and redshift in lambda CDM, you'll get a picture like this for Planck cosmology. This is the value shown in the color bar, going up to redshift 0 to 3. In terms of scale, is going to very large scale, k of 10 to the minus 2, to very nonlinear scale, 10 to the 1. Now note that this plot itself was created with linear perturbation theory, which means something like k of 0.1, beyond this, you cannot trust this plot very well. Okay, so because I have not included all the nonlinear corrections to it. And so when you go to the nonlinear scales, you cannot trust this. Effectively, if you're working with this kind of formalism, you basically have access to this range. And anything beyond, you have to work harder. You have to do higher order calculation, and then only you'll be able to use that. Although the data will be there, but in terms of theory, you can only use it to those range. Now, if I were to do this same plot again in linear perturbation theory, you start to see strong effects. For example, for f of r model, where I think I've used f of r naught of 10 to the minus 5 here, which is already, which is not yet ruled out, but it's pretty small. And so you can see that there's a significant effect, and larger effect is there in nonlinear scale. This is one of the reasons why people are really interested in trying to model this nonlinear scale. If you just stick to linear scale, the effects are very small. It start to change, so it's introduce a scale-dependent nature to growth rate, but the difference is small. And if you're able to access nonlinear scale, then you are expecting to see more stronger effects. You can also do this calculation for another model called chameleon gravity, which will show the scale dependence in different scales, at large scales rather than small scales, and then try to constrain that. So what this means is that since these models are sensitive to growth rate, what you expect if you are going to use growth rate data, you will be able to constrain these models. So that basically brings me to the measurements of growth rate itself. I've showed you several plots of this two-point correlation function in redshift space. These are all the measurements of growth rate from many different data. So we are not going to go one by one, but this is many different samples, and there's a plot, and there's a little bit of mess because not everything sort of align with each other. There's no smooth model which can explain everything, and then there are sort of systematic biases in some of them. But this is not trying to sort of choose anything, but just plotting everything which is there in the literature. And then you see there are different models being plotted with different lines. So GR2, different f of r gravity, different DGP gravity, and things like that. And you see there is a dependence on gravity model in growth rate. Z equals to 0.5. This is because it's actually all of this is from the same sample. It's a sample which is extremely well studied, and many people have tried modeling the same data with different models, different assumptions, and things like that. Which is why there are so many points. It's one of the, and you can also see it's one of the most precise measurement among all of that. And so that's why if you have a model for how to do these things non-perturbatively or at higher order, you'd go and try to test with this data set. Directly parameterize this f as in like in terms of the modification. Yes. Yeah. So if you're sort of looking for deviation, you know what is the expected form of f in lambda CDM, and so many people say, for example, one of the things I showed you is that f is omega matter, f of z is omega matter z to the power 0.55. This is a very good approximation for lambda CDM. You can say, okay, I can parameterize to the power gamma, and I can try to constrain gamma. So many paper actually does this kind of, or some other parameterization of the same thing does that. And the idea is that you want to, since now you know what is the expected value of gamma in lambda CDM, can I detect any difference? Most of the time in all those parameterization, you do not detect any difference. At least I have not seen anyone which shows a significant difference. And so you say, okay, there is no deviation. And so that's a reasonable way to look at if you're just looking at deviation where you are also model agnostic. So you don't have to write down the action and then solve for a particular form of it in general sense. But once you start making detection where there's a deviation, then you have to go back and work out, okay, the kind of parameterization you have done, what kind of action will give me that kind of growth rate difference. F of r are F6, F4, F5, these are FFR models. So this is with FR naught 10 to the minus 4, minus 5, minus 6. Predictions are quite similar. Yeah, so this is already a small value, and the range in this plot is very large. So whenever you look at this kind of thing, you have to also pay attention to the axis. aim is to constrain the parameter. For example, how much constraint you can put on FR naught at some point. If you detect, then that's great. But so far, what we are trying to do is put a stronger and stronger upper limit. Eventually, the goal is to figure out what's the model of gravity we should explain and act in our universe. That's the idea. But we go about doing that by looking at all varieties of model and see what kind of constraint we can get. To begin with, we always have upper or lower limit. And then at some point when the data become precise enough, and if there is some merit to the model, then you should detect a non-deviation. Yeah. This band is essentially a shaded region which gives an estimate of what is the error bar in this prediction itself. No, sorry, it's not the error bar. If you were to fit this data set for that particular model, then what will be the error bar in that model prediction itself? So for each model there is a band. You can't see that very clearly, but you see there is a green band as well, there is an orange band as well. But they are on top of each other. And so they are all within 2 sigma of 0. So this is the 0 line. Right, and so you can just use that thing and finally go to something like mu naught and sigma naught, which is the parameterization I showed you, and constrain this. So RSD can only constrain mu naught because it's a matter-matter interaction. It's a gravitational interaction of matter-matter, and there is no light-matter component to it. And so it cannot constrain sigma at all if you're just going to use RSD, which is why this degeneracy. If you use weak lensing along with RSD, which is the light-matter interaction, then you'll be able to constrain both. So that's the other part, which I'm not going to talk about. Okay, so so far so good. I hope this sort of give you a bit more detailed overview of how large-scale structure at large-scale test of modified gravity happens. Now let me switch gear and talk a little bit about relativistic effects. And so idea here is that I want to sort of talk about several kind of analysis being done in large-scale structure to give you a flavor of what all things people are thinking about, so that you can, when you look at literature, you have a little bit of better idea of what is happening in the community. Okay, so I have half an hour. Right, so if you want to think about gravitational redshift, to build physical intuition, this is an image of a star cluster, which is taken from Hubble again. And what you see is that again there are color, and as I told you, the color itself is coming from the composite image in different filters, right? But even in that case, if you, let's say, if you know how to figure out the color, work out how the color works out to be from the different filters, do you expect these to be the true color of whatever stars is emitted, or there is going to be physical effects which is going to change the color? So we are plotting observed color, and so observed color is going to be different from the true color. And the reason for that is that these are never true intrinsic color, because there are lots of physical effects happening. And so depending on what order you want to go to, there is going to be order of 10 or different kind of thing you can think about, which is happening, which changes the wavelength of light and shifts the color, right? And so far we have talked about 3 of these things, and I've already told you about this, so I'll skip that. One of them is gravitational redshift. And so just a little bit of history of gravitational redshift. Apart from that experiment itself, there are measurements of gravitational redshift from a spectral line from sun. There are measurements from white dwarf. And you can see these are actually very old literature, so we have been doing this for a long time. There are measurements of gravitational redshift by looking at the galaxy cluster. So if you look at the galaxy cluster, the satellite galaxies in the galaxy cluster, which are in the front of the center of the cluster versus back, is going to show you this asymmetry, because one is passing through the gravitational potential, one is not. And so there are measurements of that. But all of this is sort of is individual object or local small. If you have a galaxy cluster gravitational measurement, that's about 1 megaparsec scale you are probing. What I'm interested in talking about today is what about at very large scale, right? If you want to measure it 10, 20, or 100 megaparsec over H, can you do something with the large scale structure? What kind of quantity you're going to construct? So how would you imagine thinking about values of these things, right? So if you look at a galaxy, the observed redshift will have cosmological term. So cosmological term, imagine if you're working roughly redshift up to 1, it's of order 10 to the minus 1, which means 0 to 1, or of 10 to the power 0 if you're working beyond redshift 1. So most of the time we are concerned with redshift 0.5 or below for these kind of measurements. If you look at calculate what will be the velocities, peculiar velocities of mean peculiar velocity of these kind of galaxies, that will turns out to be 10 to the minus 3 compared to the cosmological redshift. So because it's so small, that's why we are still able to more or less measure the distances. If peculiar velocity is very large compared to cosmological redshift, then you'll not have no idea of distances of these things, right? Because that is going to dominate. So it's thankfully it's small, but and because it's small but it's not very small, we are also able to measure this in redshift space distortion, which is why you had such clear signal in that anisotropy. So thankfully it's not very small, so now we can measure growth rate. Now if you go and look at things like gravitation redshift for like a massive halo of 10 to the 14 or so, this will be of order 10 to the minus 4. So it's an order of magnitude smaller than that. And when you're going to measure redshift of individual object, there is no way to differentiate between these three. So you have order 0.1, 0.001, 0.0001. And there's no way you can separate these at all. But how would you separate Cosmo and this is 10 to the minus 1, 10 to the minus 3, right? So if this is 1, this is 0.001, this is 1% of that. How would you separate that for an individual object? But you don't know, right? It's always 0.01. It's just, this is just the order. For individual object, it might be even 0 for something living in the free space. For individual object, you have no way to separate these things because all you see is the overall effect of integration of all of these things, and anything else happens on the way. Right. So how do you sort of try to measure something like that? That's what I want to think about. Now, I think somebody already mentioned that this is symmetric along the line of sight, which is what we expect, and this is line of sight direction. And so can you think about breaking this line of sight symmetry? Because what is going to happen is that despite cosmological redshift and peculiar velocity, this is symmetric. If effect break this symmetry, then that will be easy to dig out even if it is small, because otherwise it's 0. And so let's think about what is happening when you're looking at something like gravitation redshift, which is actually one of the terms. There are 6-7 different terms which is going to affect. If you think about, let's say, dark matter halo or galaxies living in dark matter halo, one of them I'm labeling at H, one of them I'm labeling at L, L1 and L2. So this is referring to some large dark matter halo. This is some small dark matter halo. So the gravitational potential well or the gravitation redshift shown in a cartoonish way, ZG1 is larger than this ZG2. And imagine it's a perfectly symmetric system. Somehow you have such a system. So their real space positions are at R plus delta R and R minus delta R, because it's perfectly symmetric. Now if you add gravitational redshift to each of these things, what is going to happen? So if you add gravitational redshift on top of R, there is going to be ZG1 and there is going to be ZG2 attached to this, right? So all of these is going to get shifted to these red points. That's where you're going to look like. Now when you're going to calculate the distance between this pair versus that pair, they are going to look different, because now you are looking at distance which estimated through redshift, where gravitation redshift is also accounted for. For the purpose of this discussion, we are completely ignoring peculiar velocity, because peculiar velocity will give you a symmetric result in this axis. So the distance is going to be delta r plus zg1 minus zg2 and minus delta r minus zg1 minus zg2. And so this will introduce a asymmetry along the line of sight. So this is going to break symmetry. But it's not going to break symmetry in any correlation function. It's going to break symmetry only if you have such a system, in the sense that when you have one of the tracer which you are looking at is in the massive halo and have larger gravitational redshift, and the other sample you are looking at have less massive halos and smaller gravitational redshift. Then what you could hope is that by looking at this symmetry breaking, you are able to measure what is the difference in gravitational redshift in the two such samples. So it's going to be there in terms of breaking symmetry only when you are looking at cross correlation of samples which are living in different kind of gravitational environment, right? So you can construct this how much symmetry is breaking, and then so I'll tell you how to sort of construct this quantity itself. But let's say you are able to construct something like this, which is quantifying how much symmetry breaking is happening. And if you just compare different models, again the black line is GR and red line is FFR. What you're going to find is that the gravitational redshift effect for these two different model is going to different. So this is also going to be sensitive to modification to gravity or gravity model as well. So that is one of the interest. So I guess this is more detail about simulation, but maybe I'll skip this. But let me talk about. So one of the critical thing I told you is that you might be able to measure it. There's going to be symmetry breaking if you have two samples where you have different mass of the halo. So how do you go about creating two such samples? There are many ways you could think about in principle. One of the ways, let's say if you're working with dark matter halo in a simulation to begin with, for simplicity, you can look at massive dark matter halo and you can look at less massive dark matter halo. So you can divide your simulation in terms of massive halos and less massive halos. You can draw some line in between, and then if you are going to measure linear bias of these massive and less massive halo as a function of the limit on the mass itself, you're going to find that one of the sample which is less massive have low bias, the one of the sample which have high massive have high bias. So this difference in bias is actually proportional to the difference in gravitational redshift and will be proportional to the signal you are going to observe in terms of the symmetry breaking. So which is why it is important, and we are again talking about the linear bias regime here. So this is a measurement done in a simulation where we have basically said that, okay, let's assign gravitational redshift term to each of the halo, and I will look at two different halo subsample and I will do the cross correlation. So you'll do exactly what you're doing for the auto correlation, but now rather than giving the same sample, you're going to give it two different samples with certain characteristics and look at the clustering signal in exactly the same way. Otherwise, you're not doing anything else except that the things you're correlating, you're not correlating the same galaxy sample with itself, you're correlating two different galaxy samples. You're looking at cross correlation. And so if you look at the cross correlation, you're going to get this asymmetry. And so to quantify this asymmetry, you can define this. So this is just a statistics. You could have written something else, but you could define this shell estimator, which is essentially looking at if you were to draw centroids, then how much that centroid is shifted compared to the zero line. Right? So this is what we call shell estimator. You could also write down the dipole moment for this. If you know legendary polynomial, you could decompose into monopole, quadrupole, and dipole decomposition, and there will be non-zero dipole in this case because there's a line of sight symmetry breaking. So if you were to do that in a realistic simulation, and so this is now an n-body simulation rather than the model plot I showed you earlier, you're going to find that the gravitational redshift signal will look something like this, shown in the red line for a particular case. And if you were to do the gravitational redshift, there are many other effects which is going to introduce this line of sight asymmetry, because you're really talking about small effects, not into the -4. And so you have to be careful and actually calculate all these other effects. So just to name a few, this is transverse Doppler effect, this is spatial relativistic beaming, this is light cone perturbation, that is, I forgot what is this called, and this is luminosity distance perturbation. So all this is going to introduce line of sight asymmetry, and this will be of different amplitude, and what you are going to observe is the overall effect. So when you are going to model it, you have to actually work out all of these things, otherwise since if you just model gravitational redshift and try to compare that with observation, you're going to get you're going to predict things which will be wrong, and you might make wrong inference. So you can look it up in literature, the details of all these effects, which again I'm not going to talk about due to lack of time, but that's also important to keep in mind. So one more, maybe I'll skip this in the interest of time, but what I was going to show you here is that this effect I already talked about is special relativistic beaming. So when the galaxy is traveling with some velocity, if you just stop, let's say you take a spectra of a galaxy and say it's moving with different velocity, what will be the overall effect on the observed magnitude? So this is how the spectra is going to change. It's going to get amplified or suppressed in terms of flux. And it's also going to get shifted in terms of the wavelength. So this is change in spectra as a function of velocity, beta. So this is roughly 1% speed of light. This is negative 1% speed of light. So it's moving towards you and away from you. And you can work out how this will, so now this will, depending on what the situation is, it will look different in your filter. You're going to do photometric survey with a filter in it. Filter is going to be fixed in your observation frame. Depending on how the spectra is shifted, you're going to observe different magnitude. So that's where all this information I told you about the shape of the filter is going to become important, because if you have an effect like that, then your filter response function is also something you need to know to actually calculate the impact of that. And so these are the plots showing what will be the effect of this if you are looking at different bands photometry, what will be the difference in terms of the photometry itself. So you're going to see that the photometry or the flux you're going to observe is going to be different. And remember, these are like really tiny effect. I'm talking about few percent effect. Your error in these measurements are larger than few percent. And so these are not at all something we measure these days in a survey already. But in future, when we'll have many such objects with much higher depth, we might be able to measure that. So that's why these are interesting to think about. Okay, so this is something I've already talked about. I'll just skip. Yeah, so let me just show you one example exercise we did to try to measure gravitational redshift. So we took a survey. These are all the galaxies, and we took one of the R-band filter. So R-band is something I showed you in one of the filter UGRIZ images. So these are magnitudes measured in the R-band, and I said, okay, can I look at the brightest galaxies in the R-band and the faintest galaxy in R-band and split into two samples? So that's the two sample. And if you measure the bias of these things, like similar to what we did for the simulation for HALO, you're going to find different biases. And so if you cross-correlate these two samples, you expect to see the effect of gravitational redshift. Although the signal amplitude will depend on the difference on the bias and how many galaxies you have and what is the volume. So you have to estimate noise. So these are the bias estimate of these two samples when you split by R band. So you can see their biases are different. One is 2.05, one is 2.25. And so because their biases are different, you could look at cross correlation. So now you can go ahead and do the cross correlation of this survey and see what you find. So these are some null tests, but if you look at the cross correlation in R band, this is again the same estimator, which is a measure of dipole moment or the movement of centroid as a function of distance, and you find that okay, this is not entirely consistent with 0, but the noise is quite big, and if you try to fit a model to it, the model does goes through it, but it's only 2.7 sigma. So less than 3 sigma is not really very interesting. So we do see some hint of gravitational redshift, but we have not detected it significantly in this sample. But this is already a fairly old sample, and so now we have much larger sample we have already collected. So we have also done Fisher forecast with exactly the technology I showed you how to do Fisher forecast, and the models I showed you using that model. And we expect like in the next few years, if you are trying to measure this kind of effect, you'll be able to do that at least 5 sigma. If you are optimistic, then maybe 10 sigma results, you should be able to measure gravitational redshift. Not just gravitational redshift, but overall relativistic effect signals. Okay. So this sort of, this is just the same thing in terms of the likelihood, which I don't want to go over. And so this sort of covers both the topic I wanted to discuss today, which is redshift space distortion and gravitational redshift. How do you really go about measuring this? What are some of the things you might want to think about? But also key thing is that if you were interested in a physical effect, how do you go about thinking of measuring that if, let's say, that thing is not measurable in terms of the individual object level, for example, relativistic effects. So you can construct these kind of things. So you need to think harder. Statistically, can you construct things or measures to isolate certain kind of effects which might be not measurable otherwise? Okay. So with this, I guess I will just take question, and I'm finishing early today, which is good. I don't. Yes, I don't think I had anything else to say. So what I plan to do in next lecture, depending on what kind of things all of you are interested in, we can either talk about more details about errors and covariance matrices, or we can do a little bit more on the Fisher forecast, or we can have a bit more sampling about what are the other ideas being applied in large scale structure. So just let me know during the tutorial what kind of thing you would prefer. Otherwise, you already have sampling of several different things we can measure with large scale structure, and you have some idea about what are the kind of measurements we are looking at in terms of the telescope, filters, spectroscopy, and all that. So I'll take questions and we can. Mm-hmm. Yes. Mm-hmm. Yeah, so dust particle definitely will contribute to the color we are going to see. And so the way dust particle affect color is basically depending on the size of the dust particle, it can scatter light, and the efficiency of scattering light will be function of wavelength, which will be related to the size of the particle itself. And so, for example, the dust in our Milky Way is one of the things which affects all of our observation. And so when you're looking into different band and you want to figure out what the true magnitudes are, you have to apply dust correction. So for something like Milky Way, we have a good enough understanding of these distribution, and so we know the extinction coefficients we can correct for these colors. But there's going to be dust in each of these individual galaxies itself, right? And that is harder to know. So how do you figure out what are the dust content of these different galaxies? And so that is something much less known so far. I don't think there is a specific redshift where this is more important than other. What might be the case, there are different kind of galaxies for which it's more important than the other. So different kind of galaxy can have different dust content depending on the aging activities, star formation activities, and things like that. And so that is something we can model if you are able to model the spectral energy distribution of these galaxies. So if you have the spectra, when you model spectra, one of the component you try to model is what is the dust content in these galaxies. So you can use that kind of modeling to figure out what might be the effect of dust. But I don't know off the top of my head if there's a specific redshift where this will be most. Yes, so what you're going to look at is what is the observed wavelength around which, because Milky Way and us is more or less at the same redshift. And so this is all worked in the observed reference frame whenever you're working with extinction in the dust. And so that way the redshift of the object do not matter because we are locally. But if you're trying to model the effect of dust in the local neighborhood of the galaxy which is emitting light, then that will be important. So you need to know the redshift to figure out, even if you have a dust model, you need to know the redshift to figure out what will be the wavelength which will be interacting and relevant for dust correction. But that, I don't think that tells you anything about, okay, at particular redshift, this will be more or less effective. But I guess the key is that there are sort of two things. If you are talking about the effect of dust because of the Milky Way, then this will be more or less what is the observed wavelength reference frame. If you are talking about effect of dust within the galaxy from which you are observing, then you need to work in the galaxy reference frame to model the effect of dust. Yes, the supernova explosion is one of the thing. The galaxy. So let me be a bit careful here, because I don't think we have completely understood the origin of dust particle. So that is the first thing. Now, there are some guesses, and there are galaxy formation model which tries to predict this. This is the whole thing we try to do in the spectral energy distribution modeling, where we try to predict what are the kind of processes which produce dust particle. But in general, AGN or black hole activity and accretion around the AGN as well as supernova can produce significant amount of dust. Yeah. So if you want to figure out redshift, the only reliable and certain way is measuring redshift, but even that can give you wrong answer if you observe only one line, so there can be line confusion. But as long as you have detecting multiple lines, redshift spectra and redshift will give you the most precise way to figure out how where this thing is lying. Every other method, for example, for Lyman break galaxy, what you try to do is that in certain filter they will be basically not visible, in certain filter they will be visible, and so you try to look at the difference. But this can be mimicked by things like a nearby galaxy which is very dusty, and so that will be always be the cause of confusion. I don't think there is anything apart from spectroscopy to completely rule out, which is why there is always spectroscopic. There's a talk about a spectroscopic follow-up and spectroscopic sample as the gold sample, even for JWST data analysis. But unfortunately, for some of the JWST galaxies like Z equals to 16, it's very hard to do a spectroscopic follow-up.
Something blue shifting in your shell estimator. I can understand the gravitational shift. It climbs the potential, but why it gets blue shifted?
This one, right? Yeah. So this blue shifting is a function, is actually, some of it has to do with peculiar velocity itself, because when I describe this, I've completely ignored the effect of peculiar velocity. But when you have gravitational redshift and peculiar velocity, then there can be blue shifting. But also, when you look at these other effects, they do not work in the same way like how the gravitational redshift works. I didn't even describe this. And so what could happen is that the symmetry breaking, which I told you, depending on what kind of perturbation you're talking about, can be reversed. And so if it is reversed, then it will be in the other direction. So you can see, for example, one of the things for which it gets reversed is transverse Doppler effect, where transverse Doppler effect is related to what is the velocity dispersion of these halos. And so then now the larger potential was giving you larger gravitational redshift. Now the larger potential will give you smaller this transverse Doppler effect, and so it reverses the sign. But if you want to understand individually each one of them, then you have to first look at the effects and then talk about, okay, what is causing the shift. No, so that is not accounted for, and that is not important. It's because of the same reason as how we are measuring these things, right? So we are measuring relative difference between these two. So whatever happens in terms of our gravitational well is going to happen to both the galaxy, or all the galaxies you're observing, right? And since you're measuring relative difference, that effect is going to cancel out. So you don't have to account for it and subtract it individually. But we also have local motion compared to the CMB reference frame, and so that motion is also going to introduce effect. And so that is something we account for by using the appropriate reference frame when we look at the redshift. This one?
No more a background one, because in class when we look at the growth rate, it depends only on Z or redshift.
Yes.
Redshift is a background quantity. So when we go to very small scales, it's not any more a background quantity.
This is true only for non-GR model. For GR, it is independent of scale. For non-GR model, it will be dependent on scale, and so you need to modify your class if you want to. In fact, that's what I had to do to make this plot. You have to modify your class where now your growth rate will be function of scale. Yeah, so what happens is that essentially at same redshift, if you look at let's say red versus yellow, so coming from red to yellow, you're basically having a smaller growth rate, right, at same redshift. If you look at, let's say, one of these lines, it's going from yellow to green. So at smaller scale, so first of all, this is K space, right? So not configuration space. For K space, smaller value means larger scale, and larger value means a smaller scale. And so this is a small scales, and this is large scale. So for large scale, growth is at certain level, but as you go to the smaller scale, your growth value essentially increase. And so this is the behavior you expect in FFR model, where because of the additional scalar term, additional force, depending on the amplitude, the gravitational strength itself is a function of scale, right? So there's a famous factor of 4/3 in a particular FFR model, which is the amplification of gravity at certain scale, and then it goes to GR at larger scale. So this is what you're seeing essentially. You're seeing that as you go to smaller scale, the strength of gravity increases, and so the growth rate increases. No, this is not constant redshift. Redshift is on the x-axis. This black line is just the constant value. Yeah, so it will just be in the same color, right? So it's just a constant value. Yes. So we have measured at different redshift, but we do not have measurement at different scales. So what we have is that we have basically look at the range of scale, and since the data is already, even in that case, it's something like 10% measurement. These measurements, it is average over a range of scale. So now if you want to compare to the model, for the model also you need to average over the same range of scale to be, and in fact this range of scale will be different for different growth rate measurement depending on what model, what survey you have used, and so you have to be careful and use the corresponding scales for the model. Different growth rate at same redshift, I guess you mean. For different model at same redshift, different growth rate, right? Yeah. So that's what this plot shows, right? So at same redshift, any vertical line, different model have different growth rate. But as you pointed out, like for FFR models, they are very similar. That is just because the scale, and in fact, they are very similar, which is why it's hard to distinguish. The effect is small, and so which is what is hard to put a constraint stronger than what we have already. Mm-hmm. Yes. Are you talking about a specific model or just? So for a specific model, we have constraint for things like for gravity, DGP gravity. There are constraints. Sure, yeah, I can send you. So we also have general scalar tensor gravity, which the parameterization is showed. There are constraints on all of those parameters using growth rate. So those are already old, but probably somebody can update that. So we have measurement of f sigma 8 or beta, which is f over bias, depending on how you want to look at. And all of this needs to be coupled to the sigma 8. So when you're evaluating model, you can only compare with f sigma 8. So the reason we have measurement of f sigma 8 because this is because how the Kaiser formula looks, right? So it's completely degenerate. Yeah, so it's completely degenerate. This is the large scale. But if you are able to push this to smaller scale, let's say you're able to model the nonlinear scale, this degeneracy can in principle be broken. And in that case, you will be able to measure f and sigma 8 both. Or another thing we often do is we combine this with the lensing data, which will also have a measurement of sigma 8 apart from. But the current RSD measurement from a spectroscopic survey have measurement of only f sigma 8 so far. Sorry, what do you mean? This will have a non-zero quadrupole if you are going to project. Yeah. So in this formula, in this linear theory, you can just expand this, right? So if you just expand this, you'll see that there's going to be hexadecapole, but nothing beyond that. It's just the power of mu, what you have here. Those are the moments. So there's going to be no odd multipoles because it's symmetric along line of sight, but you'll have even multipoles. You'll have monopole, quadrupole, and hexadecapole. There's going to be no dipole or tripole because this is symmetric along this axis, right? So if you write down your legendary polynomial, if this is symmetric along x-axis in this angular space, your dipole moment is going to be 0, or any odd multiple moment is going to be 0. In fact, that's one of the things you're going to do in tutorial, where once you measure this in redshift space, you're going to project it into multiple moments. So you're going to do legendary decomposition of that, because we want to look at monopole and dipole, and that's how we model these quantities. Thank you.